Up here we have the two equations that we had at the bottom of the previous slide, and recall these are now taken from the partial derivatives, these two here, where we found the partial derivative of the Lagrangian with respect to x and the partial derivative of the Lagrangian with respect to y. Okay, and if we rearrange both of these, we will end up with lambda equals u subscript x over p subscript x, and on the side lambda equals u subscript y divided by p subscript y. So let's just think about what we have here with the u and the p. And going back to this partial derivative here, all right, remember it's obtained by partially differentiating the Lagrangian with respect to y, and u subscript y, this is obtained from partially differentiating the utility function part of the Lagrangian with respect to y. And recall from our earlier studies when we were looking at the derivative, the original function we consider the total function. So in this case we're looking at total utility, and when we find the derivative we will be finding the marginal function. Alright, so in this case here, when we are partially differentiating total utility with respect to y, what we are finding is marginal utility of good y in this case. So it's telling us if the consumer increases their consumption of good y, what their addition to utility will be, which of course we know to be marginal utility. All right, and p of course is the price of good y, which we are given. All right, so that's what we have here, and for both of these partial derivatives, having rearranged, we have lambda equal to something. All right, so we can set this equal to this, okay, because they are both equal to lambda, and remember of course that this is a system of simultaneous equations. All right, so we can set all of this equal to each other, and by rearranging we end up with the marginal utility of good x divided by the marginal utility of good y equal to px over py. And thinking of these values here, right, these ratios here, if we think back to consumer theory and indifference curves and the budget constraints, which we'll see on the next slide, these ratios here will give us the equilibrium condition. Okay, it's at this point where the marginal utility of good x divided by the marginal utility of good y equals to the price of good x divided by the price of good y. It's at this point that the indifference curve and the budget constraint are tangent to each other, and it's at that point that we have the consumer equilibrium. All right, so we need to continue, and we're going to find the total differential of u. Okay, so u being our utility function, total utility. All right, and finding the total differential of u, okay, we would end up with this, and we would set it equal to 0 because recall utility is constant along an indifference curve. All right, so utility would not be changing. The change in utility would be 0, all right, along an indifference curve, even as the combination of x and y are changing. Okay, the amount of good x, the amount of good y that you are consuming might be changing, but total utility would stay the same. All right, so rearranging here now, we would end up with what we have in this bottom line here. And the important thing now is that we have a negative sign, okay? So marginal utility of x divided by marginal utility of y. So it's the same as what we were able to calculate, the same value that we calculated up here, but we have a negative sign, which is of course important because if we think of the indifference curve and the budget constraint, these have a negative slope, as we'll see on the next slide. What we have sketched on this graph is an indifference curve and budget constraint, and what we have been working out is nothing other than the tangency condition. Okay, we know that where the indifference curve is a tangent to the budget constraint, that is the equilibrium position. All right, and at that point there, these two ratios, marginal utility and price, will be equal. All right, so what we've been able to do is working with our Lagrangian function and partially differentiating our Lagrangian function, we've been able to work with the partial derivatives to derive the ratio of the marginal utilities and the ratio of the prices, which we know to be our equilibrium condition, the tangency condition. All right, and the ratio of the two marginal utilities, that is the slope of our indifference curve, and we refer to this ratio, if you recall, as the marginal rate of substitution, and the ratio of the two prices is the slope of our budget constraint. The remaining slides, you will see some examples that you are encouraged to work through. Whilst the solutions or suggested solutions are provided, you are encouraged to try to do these on your own first. So we won't go through these in too much detail together because it's the same approach that we've been discussing in the slides up until now, but perhaps just to highlight a few things. So in this example, you have a utility function subject to a budget constraint, both are given up here, and you're asked to use the Lagrangian multiplier to find x and y such that utility is maximized, and then you are asked to find the marginal rate of substitution. All right, so starting with question A, very standard approach, set up your Lagrangian function and work out your first order condition. All right, something that's slightly new now is in this suggested solution, and you can be asked to do this, you could be asked to solve for lambda x and y using Cramer's rule. All right, so instead of using the substitution method that we did in the previous examples, here we are using matrix notation. So your starting point is to set these equations out in matrix notation and then use Cramer's rule in order to solve. All right, and the calculations, which again we won't go through because we did cover these in an earlier session, but the values, okay, for the determinants are as follows, and then you can work out the values for lambda, x, and y. All right, and the next part of this question is then to confirm that you have a maximum. So we are now looking at the second order condition, and your starting point is to set out the bordered Hessian. All right, so that has been done for you here. All right, but obviously you need to work through this and make sure that you can do it yourself. And then calculating the value, the bordered Hessian, can obviously choose the row or the column that you want to work with. And here you get a value of 24, which is positive, and we therefore know that the equilibrium is a maximum. All right, so very straightforward approach, similar to the examples we've been working with up until now. The second part of the question, where you have to work out the marginal rate of substitution, here you would want to use the total differential. Okay, that would be the approach to use, because not only will you get the correct value, all right, of the ratio, but you also get the correct sign, okay, which in the case of utility maximization, the tangency condition, we will have a negative sign. All right, so it's working out the total differential, okay, substituting in for these partial derivatives here and rearranging, okay, you will end up with y plus 1 divided by x, and this is where you need to go back to the values you calculated for x and y, substitute in, and you will get a value of minus 3. And you can double check yourself, because you know from what you were given in the budget constraint, the ratio of the two prices, good x to good y, is 6/2, so you will be getting the same value. Okay, so that indicates here that effectively we would have satisfied the tangency condition, or worked out the value of the ratios at the equilibrium. Our next example is also a utility maximization problem, but here we have the Cobb-Douglas functional form. So our utility function now appears in this form here, and we are still subject to the budget constraint, but our approach is the same. All right, the starting point is to set out the Lagrangian function. The next step is to work out the first order condition, and for that we need to find the partial derivatives of L with respect to lambda, x and y, and we see those here. All right, and then using this set of simultaneous equations via substitution, all right, we are able to work out the value for x and y. Okay, so obviously here we are not using Cramer's rule as was used in the previous example. We have gone back to using substitution, and here we've got Lx, right, and Ly, all right, and taking the terms with lambda across to the other side in each case. And then what they have done here is leaving this equal to 8 lambda and then multiplying through, or multiplying both sides by 4. All right, so we get something on the left-hand side equal to 8 lambda. All right, and we can then set these equal. All right, so multiplying the left-hand side by 4, 0.25 times 4 will give you 1. All right, so you're left with a 1 in front here. And then working through this, we see that y equals 0.4x, and we can then substitute this into the budget constraint. All right, and we can then work out the value for x, all right, and then take that and substituting back here, we'll be able to work out the value for y. All right, so you're obviously encouraged to work through this and see that you can get these solutions. And this particular example just ends here with you calculating the values for x and y. All right, the final example for you to go through is an application now using logs. So you'll see again, the approach is the same, But now you need to remember what you have learned about logs, all right? Because you've got your utility function, all right? And you can see we've got some natural logarithms here, all right? And subject to an income of 36, and the price of good X is 2 and good Y is 4. Okay, so you also need to set up the budget constraint. So your starting point, again, is to set up the Lagrangian function, right, which is the utility function here, plus lambda, and then in the brackets would be 36 minus 2x minus 4y. All right, because our budget constraint would be 36 equals 2x plus 4y. All right, so we would need to set up in the brackets as follows. All right, so just to go through this, you've been asked to find the values of x and y that maximize utility, find the marginal rate of substitution, and check the second order condition. All right, so very similar to, well, the exact same approach as what you've been adopting in the previous exercises, but now you need to remember to work with your logs, and particularly how to differentiate, because obviously now when it comes to differentiating x and y, you're going to have to differentiate these terms that include the natural logarithms. And remembering your rules, okay, when you have a natural logarithm, okay, of x, the derivative would be 1 over x. All right, if you differentiating with respect to x. Differentiating with respect to y, you would end up with 1 over y. And we can see that down here. Okay, when finding the partial derivative of the Lagrangian with respect to x, okay, 1 over x, but remember we've got this 2, all right, that will stay with, and it will be 2 divided by x. All right, for here it will be 1 over y. All right, and thereafter it's calculating the value. You are asked to calculate the value of x and y, so that's what you have here. And again, this is by using substitution, using these three equations here. All right, you using these two, first of all, we work out that x equals 4y, and then substituting back into the budget constraint, you'd be able to solve for y and then calculate x. All right, so that's how you would get these two values here. All right, and then we are asked to find the marginal rate of substitution. Once again, we would need to find the total differential du. All right, and at this point should be a fairly straightforward calculation, and we would be able to check this value here that we get for the marginal rate of substitution, checking it against the ratio of the two prices. All right, and finally we need to work through the second order condition, and that is to check that we have a maximum, because again we are working with utility, so it's about maximizing utility. So our starting point needs to be to set up the bordered Hessian, all right, and that is what is shown here, and working out the value of this determinant, we get a positive number, which we know would indicate that x and y indicate a maximum.